We are looking at section 9.3 here in Unit 5, thinking about our next section. It's about paper folding. So they tell us that the thickness T in millimeters of a folded sheet of paper after it's folded n number of times is given by the equation T equals 0.05 times 2 to the n. So we're looking at an input of number of times we're going to fold something and an output of how thick that stack gets. So I've got this little piece of paper here just kind of give us a little demonstration to see how this works. So it asks us first, what does the number 0.05 represent in the equation? And that right there, we've seen our kind of format of what these look like, where we have our starting value times our multiplier, also known as our factor, and it's raised up to an exponent for how many times we repeat it. So that idea, that's like how many times we repeat the cycle. So in our format that we see going on, we have each of those parts, and the 0.05 is telling us our starting value. So it is that the paper starts with a thickness of 0.05 millimeters. So put the mm for millimeters. So one layer of paper is 0.05 millimeters thick. And this starts to make sense that we're going to now be multiplying it by 2 every time you fold it. Because if I fold it one time, that thickness now doubles, right? It's 2 layers of paper that are each 0.05 millimeters thick. And if I fold it again, then I have something that is 4 layers. Right, so I went from 2 layers to 4 layers. Now it's 4 layers that are each 0.05 millimeters. And if I fold it again, those 4 layers become 4 layers on top of 4 layers, or 8 layers. So it multiplies by 2 again. And you can understand how this is now starting to get thicker and thicker and thicker the more we fold. Now part B asks us to use graphing technology to graph the equation T equals 0.05 times 2 to the n. Now you can do this on your graphing calculator if you're here in class and have that. So I'm going to show you how to do that, but we can also use Desmos. So I'll show you that because Desmos is what you're more likely to have with you right now, and we'll use that Desmos to answer our questions, okay? On our graphing calculator, we could go to this y equals right here, and it will show us a graph a lot like Desmos, but I'm going to use our Desmos because that's what we see. So let's see, I want to go here, and I'm at desmos.com, so I'm going to go to the graphing calculator. And I just like that mode better because I can see better. I'm going to type in our equation, 0.05 times, so I need to use my keyboard because I'm going to multiply it by 2, and I need to raise it up to the, so I'm going to use this button here for the exponent, raised up to the, and because it doesn't understand n and t, I need to use x's and y's so that it can show up on Desmos. So here I am on Desmos, 0.05 times 2 to the x power, and I can see what my graph looks like. So let's take a moment to sketch what that graph seems to look like on our paper so that we see it here. All right, so we can see that it's an upward sloping graph, and we'll be able to sketch in some answers to the rest of our questions if we have that sketch. So down here, I'm going to sketch that in. It never went below the x-axis, so I don't need to have anything below there. And it's got this upward slope, and then it kind of goes down like this and gets closer and closer. So I'm going to keep my Desmos open so you can see how this works. How many folds does it take before the folded sheet of paper is more than, greater than 1 millimeter thick? All right, so let me start there by thinking of more than 1 millimeter. So right now, everything that we have is measured in millimeters. And so I'm going to go to my Desmos screen again, and I'm going to put in a y equals. Now this is because I want my output to be 1 millimeter. So I'm going to put y equals 1 millimeter. So here is that value at 1 millimeter, and I can see that it crosses here, and I can use Desmos to find that point very quickly. Now it says it takes 4.322 folds, but we need to be smarter than what Desmos is telling us. So we put in a line here like this at 1 millimeter, and we found that that point crossed at 4.33, I think it was. Let me go back and check that real quick. Yep, 4.32. And that's when it's 1 millimeter thick. Now we can't do 4 1/3 of a fold, because that's not going to get us the thickness that we're looking for. I don't know what 1/3 of a fold looks like. Bringing the paper 1/3 of the way over. Well, that's not a thickness of 1. We have to round that up. So it's okay if it's more than 1 millimeter, but it can't be less than. So at four folds, it's too low. By the 5th fold, it would be high enough. So 1 millimeter would take 5 folds. So I'm going to put a little star down here with an asterisk to remind myself that we can't do a partial fold. So technically, our graph shouldn't be a continuous line here, because all of our inputs, we can only do whole number folds. So we should actually see a series of separate dots like that instead of one continuous line. So if I put that information, I think there's a way that I could type that in here, like with all of my x values, such that x is only whole numbers. I can't remember how to type that in on Desmos, but there's something like that where we can like make sure that x is only the real numbers and whole numbers. So anyway, we get that idea that I can't do a partial fold. Now this question also asks us, back over here, what about how many folds before it is more than 1 centimeter thick? And so I'm going to switch colors of my pencil to think about that. 1 centimeter, I'm going to just give you this equivalency. 1 centimeter is 10 millimeters. So as soon as I have 10 of those millimeters, I would have 1 centimeter. So I need to find out when we would have this line equal to 10. All right, so 10 millimeters is up there. All right, so I need to go back to my Desmos, and I need to change this where I wanted it equal to 1. And now this time I want it equal to 10. And my horizontal line is off my screen, so I just need to slide it down so I can see that line at 10. And when I click here, I see that it's going to take 7.6 folds. But again, I can't do a partial fold, so I have to round that up. It's okay for it to be more than 10 millimeters, but it can't be less than. So I'm going to go to that rounding up to make it more than. So when we did this, we found that point was So that would take 8 folds to make that happen. So graphing technology tells us that kind of stuff. We find those intersection points going on here. Part 2, when we think about the paper folding, question 2. The area of a sheet of paper is 93.5 square inches. Remember, area is just length times width. Find the remaining visible area of a sheet of paper after it is folded in half once, twice, and 3 times. So I'm going to make a table of values. And I'm going to think about how many folds we have and what our area looks like. And so with 0 folds, we have 93.5 square inches. And as soon as we fold that piece of paper in half, whatever size that it is, if we're looking at the visible area of a piece of paper, if we fold it in half, the area cuts in half. So I'm going to use that 93.5 inches, and I'm going to multiply it by 1/2. Okay, because our folded area, when it cuts in half, we see half as much of that paper. So now I am going to go to my calculator. 93.5 times 1/2. That's how we would put that as a fraction on our calculator. And after 1 fold, it would be 46.75 square inches. Now after another fold, it's going to take that amount and it's going to cut it in half. So I'm going to times it by 1/2 again. And that's going to help me find my next value. So again, I'm going to take my answer. I'm just going to hit the times button because that'll take this answer and multiply it by 1/2. And we get 23.375. And I need one more time because it asks up to 3 times. So I'm going to take my answer again, multiply it by 1/2, and we get 11.6875 square inches. And yes, I could have multiplied that by 0.5. It means the same, so you're good to go. So if we're writing an expression for the visible area A is our output, in terms of the number of times it has been folded, N. Well, we need to go back to our idea up here. We need a starting amount and a factor raised up to the number of times we're folding it. And we start with a paper that is 93.5 square inches. We found our multiplier. That's our factor, 1/2. And we're doing it every single time we fold that paper, so we're going to raise it up to the nth power. So it asks us to use graphing technology to graph this equation. Let's go back to our Desmos screen. I'm going to turn off that one. And I'm going to write our new equation, 93.5. Sorry, forgot that. In parentheses, I've got 1/2, 1 divided by 2. And we're going to raise it up to the x power. And I'm going to scroll back a little bit so we can see this. That at the top, oh my goodness, I have to scroll back a whole bunch, which means I should, instead of scrolling and moving it around, I should go change my values. I want to see a y maximum that starts up at like 100. Now I knew that number because over here we're starting at 93.5. So starting with 100 lets me see there's that vertical intercept at 93.5. And it's cutting in half every time we fold the paper. So let's sketch that graph in our workbook. It starts up here at 93.5. it's got this downward swooping thing that cuts in half for a certain number of times we fold. So this shows that I use graphing technology and I graphed it in this context. Can our graph take negative values? Well, Desmos thinks that it can. See how it's going to negative x's over here? So it's saying that we can have negative x's. But if I think about in context, it really doesn't make sense to have negative x's. And to explain my reasoning, that would mean I have negative folds. I don't know what a negative fold looks like. I can only unfold the paper until I'm back to my starting area. And I can't unfold it any more than that. So, no, n cannot take negative values because we cannot fold something negative times. The area cannot get bigger than it starts. And so now it's asking in part E, our last question here, can A take negative values? Can we have a negative area? So we drew this where it gets closer and closer and closer to 0, but can it ever cross that x-axis and go down? Let's go look at Desmos. It hits our value here, but even if I hold it and trace, do you see how there are still values? Even when it looks itty-bitty teeny tiny down here, it is still taking a value. Now again, Desmos shows us that it can be 0, but that's just a rounding thing. Now what it never ever does is it never turns negative. Okay, so it'll get really, really, really close to 0, but it will never go negative. And I'm going to say again, no. The area cannot be a negative value. I really don't know what a negative area might look like. That might be a black hole out in space. I don't know. I think we're breaking science at that point in time, so I think we should stop. All right. So you might be like, black hole? Maybe? We just can't have a negative value. It's just not going to happen. All right. Breeze through that summary that we have there. Section 9.4 is an info gap. We're not going to do that part, so cross that part off. And you can review this stuff here. You see those series of points that we talked about if we're looking at those. Thanks, guys.